Welcome back, AP Statistics, to the fourth installment of Chapter 12. We're continuing our discussion on experimental studies. So, in general, the best experiments are comparative. That means the study needs to compare the effects of multiple treatments, including a control treatment. Okay? So, at a bare minimum, an experiment must have at least one control and one treatment group. A failure to have a control group makes the study absolutely worthless. You need a control group for the sake of comparison. So any study that just wants to see the effects of several treatments without a control group is worthless. The best experiments are double-blind. Remember from last video, we talked about blinding. Double-blind means neither those who are involved in producing or gathering the data, those who I said have boots on the ground, as it were, they are actively involved in the gathering or producing of information, nor are those who evaluate the data, like, say, taste testers or judges or physicians, seeing if the dog food we've mentioned in the last couple of lessons is okay or whether it's still contaminated. So neither those producing or gathering the data nor those who evaluate the data know which subjects received which treatments. If we double blind, we minimize our possibility for bias. And we want to randomize. Subjects are randomly selected to receive treatments, again, to avoid bias. And finally, placebo-controlled. The control treatment should involve a placebo. So, randomized block design. Here we're going to take two of those elements that we've already talked about, randomizing and blocking, and put them together into a common design for an experiment. So, suppose in our study of tomato plants, so we're growing these tomato plants, and we are seeing whether this OptiGrow fertilizer produces tomatoes with better qualities. So suppose in our study of tomato plants, we got 12 from store A and 6 from store B. You might have an idea of where this is going. Plants from the same store may be similar to each other, but different from plants from another store. And that means that we should use the technique of blocking. We have two blocks implicit in our data. We have 12 from store A and the 6 from store B, and we think that they may be fundamentally different because of the store they came from. So keeping this in mind, we would want to randomize treatments within each of the blocks, within the plants from store A and the plants from store B. Now, what does that mean? Instead of administering randomized treatments to all 18 plants together and risking a disproportionate number of store A plants or store B plants in our treatments and thus messing up our data, randomized treatments are administered to the group of 12 from store A and then separately to the group of 6 from store B. That way, the plants from each store would be represented equally among the treatments. This process is called a randomized block design. We are randomizing in the context of blocks rather than our sample of 18 tomato plants as a whole. And if you're anything like me, you would want to see a picture of how this looks because this is admittedly a little bit confusing. So check out this picture, which looks confusing up front, but it's actually really helpful. So we start out with 12 tomatoes from store A and 6 from store B. This is straight out of your textbook, by the way, if you'd like to see. Block A has 12 tomato plants. I want to make sure that they are evenly dispersed among the three groups, because each one of these groups is going to receive a different treatment. We have a control treatment for these 4 plants here, a half-dose treatment for these plants right here, and a full-dose treatment for these plants right here. And then we would compare desirable qualities. Then we go to block B, which has 6 tomato plants. We have 2 in the control group, 2 in the half-dose treatment, and 2 in the full-dose treatment, and we compare them amongst each other as well. And the power of this is that we make sure that 4 plus 2 equals 6 total plants are in the control group, 4 plus 2 equals 6 plants are in the half-dose group, and 4 plus 2 equals 6 plants are in the full-dose treatment. Doing it this way makes sure that we don't have a disproportionate number of block A, 12 tomatoes from store A plants in one of the treatments, or a disproportionate number of the 6 tomato plants from store B in any of the treatments. So let's apply our randomized block design in another example. So in 2007, the pet food contamination put cats at risk as well as dogs. How unfortunate. Our experiment should probably test the safety of the new food on both animals. Absolutely, don't want any of our pets getting sick. So why shouldn't we randomly assign a mix of cats and dogs to the 2 treatment groups? What would you recommend instead? Think about what the problem of this would be, assigning a mix of cats and dogs to the treatment groups, and what would you propose to do, perhaps using this idea right here. Give it a thought, see what you come up with, and then check your answer against the answer in the book. All right, let's continue. Dogs and cats may respond differently to the food. They are literally different species, so they may have a different response. That variability could obscure my results. All right, we don't want needless variability. There is a completely sensible decision we can make. Blocking by species can remove that superfluous variation. So we have a block for just the cats and a block for the dogs. You randomize the cats to the 2 treatments separately from the dogs. And then you measure the responses separately and look at the results afterwards. So we have a block for cats, a block for dogs. Randomize the cats among the treatments, look at your results. Randomize the dogs among the treatments and compare your results. All right, and now we're going to talk about among the most common methods of performing an experiment, the matched pairs design. So for small samples for which there are 2 treatments, you have a control and some other treatment, so very simple situation. One particularly common model that involves blocking is called a matched pairs design. So this design pairs subjects according to some common characteristic, and one from each pair goes to each treatment. That is, you pair subjects that have some common characteristic. One is randomly assigned to one group, and the other is automatically assigned to the other. This is very common in studies among twins. So you have pairs of twins, and you randomly decide which twin is going to go to the control and which twin is going to go to the treatment. And we like to do this with twins because twins are genetically similar, so they'll likely respond in a similar way. All right, so when we have pairs of twins, this is a great idea. For example, suppose that an experiment was being conducted to determine whether the new brand of puppy food improved the health and development of puppies. Suppose that a litter is available for study and contains 10 puppies, 4 male and 6 female. Since male and female puppies may respond differently to the food, we could pair the male puppies. For each pair, we could send one at random to the control group and another to the treatment group. All right, so we pair 2 males, send one to the control at random, send one to the treatment at random. All right, we have our next 2 males, send one to the control and one to the treatment. All right, on to our females. We would break that into 3 groups of 2, and we would randomly choose from those groups of 2 who we're going to send to the control and who we're going to send to the treatment. Now, up to this point, we've only been dealing with one factor at a time. Although I think I hinted before that you can have more than one factor, more than one explanatory variable in an experiment. You just have to be careful in how you do it. So this is a bit more advanced than what we've talked about before, but it is worth mentioning because it is totally something you can do in the context of an experiment. So suppose for the tomatoes experiment, in addition to the 3 levels of the factor fertilizer, we were going to throw in 2 levels of another factor, irrigation. Namely, we could have let the rain take care of the irrigation, let nature do what it does. And number 2, we could also water the plants daily. We could take matters into our own hands in terms of what water the plants get. So now we have 2 factors, 2 explanatory variables. We have the fertilizer and we have irrigation, right? So we can model an experiment with multiple factors using a 2-way table. All right, so this will look a little familiar. We see there are 6 possible allocations for each subject. And since the allocations are randomized, such an experiment would constitute a 2-factor experiment. So that randomization makes it a true experiment. Okay, so here's how we'd model this. We have one factor is the fertilizer, and that has 3 levels. And the other factor is the irrigation. We say no added water versus daily watering. And we see that there are 2 times 3 equals 6 different groups. So there are 6 different groups of individuals here that we're going to need to consider. We're going to need to divide up our sample into those groups. So here's how we could do it. So we start with, say, 24 tomato plants from a single garden store. Let's keep it simple. We're not going to have store A and store B here. So we have group 1, and we say 24 divided by 6 total possibilities equals 4 plants. And they are going to be the control treatment, and we're going to let nature do its business. In the second group, we have 4 more plants, and we have a half dose and let nature work. And 4 plants, treatment 3 is full dose, and we let nature work. And groups 4, 5, and 6 are the control, half dose, and full dose, but with us actually doing the watering. Okay, and then we take all 6 of these treatments and we compare. So we can see whether the control, half dose, or full dose are more effective with watering via nature or with watering via the watering pail or some other thing we could set up. I don't know. I'm not a farmer. Now we're going to talk about confounding. Confounding, right? So confounding is kind of like lurking, okay? Do you remember the lurking variables from way back when? This is a confounding variable. It's similar, but there is a key difference, and we'll talk about it. So here's another experiment. Suppose a local police department conducted a study on the average speed of drivers on a busy street, and they altered the factor police presence with 2 levels. You have a minor presence versus a major presence. All right, so this is a hands-on study. We have a factor, an explanatory variable that has multiple levels. However, suppose the police observed minor presence in the morning and major presence in the evening. This opens up a can of worms, does it not? Perhaps drivers drive differently depending on the time of day. Perhaps they're rushing to get to work. Perhaps they're taking their time getting home. Perhaps they're rushing home and taking their time getting to work. I don't know. But we would say the variables police presence, which may have some effect on the speed of drivers, and also time of day, which may have an effect on the speed of drivers, are confounded, meaning that they are 2 variables and we can't tell which actually affected the driver's speed more. So let's apply our knowledge of confounding. After many dogs and cats suffered health problems caused by contaminated foods, we're trying to figure out whether a newly formulated pet food is safe. Our experiment will feed some animals the new food and others a food known to be safe. And a veterinarian will check the response. So here's the question. Why would it be bad design to feed the test food that's the food we're trying to figure out is good or not, to some dogs, and the safe food to cats. Think about how that could produce confounding. Pause the video and unpause the video when you think you have an answer. Okay, assume we're ready to continue. Let's go. This would create confounding. Well, you don't say, that's what the slide is called. Let's see how it happens. We would not be able to tell whether any differences in the animal's health were attributable to the food they had eaten, that's what we're trying to figure out, or to differences in how the two species responded. So it could be that the food itself causes a difference or it doesn't cause a difference and we have fixed our pet food problem. Or that there could be a difference in how cats respond to the food as opposed to dogs, all right? So the variables food the animals received and species of the animal are confounded. We can't tell which actually has the most effect on the health of the animals, which is our response variable. So to end our lesson today, let's talk about the difference between a lurking variable, which we've discussed in a prior section, and a confounding variable. So in an observational study, a lurking variable is a variable we are not considering that creates an association between two other variables. So let's look at this picture over here. Here's our lurking variable. Here are two variables we think are related. Now, a little bit of research might indicate there's some kind of relationship between x and y, but really what's going on is that there is some variable we're not studying that has an impact on both of these variables in such a manner that it looks like x and y are related. There's an association. Maybe as x increases, y increases, or as x increases, y decreases. And we see that association and we think it's really neat. But it's actually the impact of the lurking variable on both of these variables that makes it look like there's a relationship when there's no actual good reason to think those two things are directly related. They're just both related to the lurking variable. So researchers might falsely suppose there's a relationship between two variables when a lurking variable is actually causing that relationship. In an experimental study, now notice, lurking variables exist in the context of an observational study and confounding variables exist in the context of an experimental study. That's a really good way of telling the difference. But in an experimental study, a confounding variable is a variable we are not considering that affects the results of the response variable. All right? So we have this experiment. We want to see if there is a connection between x and y such that changes in the variable x have some effect on the variable y. Well, here's another variable we're not studying, and changes in it may affect the variable y. Well, which one is affecting y? Is it the one we're studying or the one we're not? Maybe it's both. We don't know. And that's the trouble with confounding variables. Researchers can't tell whether the confounding variable is in part or fully responsible for the results of the study, which makes it, well, confounding. But don't be confounded about this homework assignment. Ooh, that was terrible. Okay, I gotta be done. Have a good day.